you have one last homework that will be due next week as well. And the test is on the 17th, if you remember. So here the first question was about testing. We have two samples, a sample from a distribution X and a sample from a distribution Y. The sample size for the population X is 13, the sample size for Y is 16, and you need to test the hypothesis H naught mu X equals mu Y versus the alternative that mu X is less than mu Y. The assumption is given sigma 1 squared equals sigma 2 squared. You need to know there is a big difference between sigma and S. It is not S that is equal, but the sigma squares that are equal. So you have sigma square 1 equals sigma square 2. Once that is set, you know that your test statistics needs to use the pool sample to estimate the variance because it is not given. All you know is that they are equal. So combine the sample, you combine the samples to find the pool variance, which is obtained by the formula n minus 1 s1 squared plus n2 minus 1 s2 squared over n1 plus n2 minus 2. And you form your test statistic, therefore, using that SP in place of sigma. Therefore, you get x bar minus y bar over SP square root of 1 over n1 plus 1 over n2. So this is the test statistic. And if we call n equal n1 plus n2, then the degree of freedom of this random variable is n minus 2, which is the n1 plus n2 minus 2 that you have down there. And you would reject h naught based on what is there. If t is less than c, such that the probability that t is less than c is equal to alpha, the probability to reject the null hypothesis under the null hypothesis is equal to alpha. That's the definition. And from that definition, you can find C. It's therefore negative t.05 with n minus 2 degrees of freedom. So that number is negative 1.703. Now, if you take the problem and flip the things that are written here, change x and y here, then you need to be very careful with the way you're handling the test statistic. Because if you flip them, you're going to be looking at a different number here. Flipping these two numbers will still have a t statistic, and it will still have a t distribution. But now the way you are deciding here, it's got to change. Because you need to relate what you're doing here to the hypothesis that is written here. Now in part B, they gave you the data. So that is x bar, y bar, s1, s2. So you need to plug them into the formula to get what the t statistic equal to. You get t equal negative 0.87, and that is c. And your rejection rule is you reject if t is less than c. Unfortunately, in this case, t is larger than c. So you cannot reject h naught. You don't have enough evidence to reject h naught.
What happens if t and c are equal?
You reject if you have t strictly less than c.
So,
And it's really a very rare case to be thinking. As you know, for continuous distributions, the probability of having equality is 0. Okay. So for you to have data in which you will be having equality, it's really a rare case. Now, in the second question, it is about proportions. So there is a belief that a proportion is equal to 0.14. You run 590 experiments independently and record 104 for Y. And the question is, was this campaign successful? And the goal of the campaign was to make sure that P is larger than 0.14. So if you want to know if the campaign was successful, you want to know whether after that campaign your P remains 0.14 or gets better. So your H0 is what you believe it is, and the H1 is the desired outcome. You want to make it better in the problem, so you're trying the alternative against P larger than 0.14. Therefore, in what you have in your book, P0, that's the value you're testing against, that's 0.14. And your critical region needs to use a Z statistic because here you're testing for a concrete value. So you're using not an estimate here, but the value you're testing for under H0, P0. And P hat is defined in your notes as Y over N, number of successes divided by the sample size. Therefore, that Z statistic is actually this, Y over N minus P0 over square root of P0 times 1 minus P0 divided by N. And your rejection rule, that's here, larger than, so you're rejecting if you're larger than 2.325, which is the Z of 0.01. You reject H, and if this Z, that Z is the one that is defined here. And this is what you would call the rejection, the critical region in the problem, Z larger than this, which means this quantity larger than 2.325. So what is written here is actually that statistic, right? So it's not the Z from the Z table that you're seeing there, it is this. And the last part of this question is asking you to find a p-value. So what we call the p-value is the probability of the extreme case, which is the observed value. The observed value of your Z is this, so you compute that observed value and you try to find the probability that your standard normal is larger than that value that you compute based on the data. So the quantity that is here is that test statistic computed for the given sample. That's by definition what you call the p-value. Now, when you compute that and you look for this probability, you get to your Z table to find out what that probability is equal to. Now, what's your decision? You can give the decision based on the p-value. You can give the decision based on the critical region. What does the critical region say? You reject if Z is larger than this, right? And what is Z equal to? 2.54 is 2.54 larger than this? Yes. So you reject H naught. When you base your decision on the p-value, we say that we reject when the p-value is less than alpha. And in this case, your p-value is 0.005, and that's definitely less than 0.01. So either way, you will reject the null hypothesis. Any questions on this? There is a question now, it's the time to understand. Yes.
What's the definition of p-value? Is that 2.54 or is this the z alpha?
This is the number that is computed together. The value of the test statistic based on the data. So that's the best or the worst case scenario given the data that you obtain. What would the chance to reject the null hypothesis be based on the numbers that you got? That probability is what you call the p-value. And based on what you got, you compute this. And then you put it in that formula right here. And you find out what this probability is. That's a very important moment. And this is done for 3 cases. Here we tested, for example, in this problem, it was less than. In the second one, it was larger than. You can look and see the difference between what we did up there and what we're doing here. And there is a third case when the alternative is different. In that case, you need to take twice the probability because you have 2 tails. Any other questions? So the next problem is about the chi-square test. And you want to be very careful when you're answering questions with this. You can do a work and apply formulas, get the correct numbers, but what you are doing doesn't make sense because in words, you explain the wrong way what you are doing. In this problem, for example, it says that we are comparing 2 multinomial distributions, which means this is one distribution, that's another distribution, and we want to know if this distribution is the same as that one. So you cannot consider this as a 2-way table in which you're just computing the chi-square distribution and testing for independence. That's not the same thing. Though the work that you'll be doing will look like it, it's not the same meaning. So if you start here and you start telling me you have degree of freedom 2 minus 1 times 5 minus 1, starting from that concept, there is a problem. Because you're assuming that's the 2-way table, and then you have 2 minus 1 here and 5 minus 1, but that's not what is going on. What's going on here is you have 2 distributions completely different, and you're testing whether the proportions that you're getting there are the same or not. So you're testing this probability equals that, probability here equal this, probability there equal that, and so on, right? But if you don't read carefully the text, you can think that you're using this to test for independence, right? Of 2 traits, one here and the other one here, where you're testing whether P of A I Bj equals to P of AI times P of Pj. So you got to be careful when you're reading the problem to know exactly what's going on and why you are doing what you're doing. That's what I needed to explain in this. So in this case, you have k equals 5. That's 5 levels of the multinomial. And you're comparing two distributions. So the df is k minus 1. And now the estimate of each of the pi1, pi2, because you're assuming that they are equal, they will have the same estimate, which will be the pool estimate of those things. When you pull them, the sample sizes get added, and the number of successes gets added. That's how you understand the formula. So that's why this is true. And you're pulling that back into your formula of the chi-square that we wrote, which would be xij for the position where you are, minus n times p. And the p is what you got here, squared over n times p. And then you plug in those numbers and you add them, and this will follow a chi-square, approximately a chi-square distribution with k minus 1 degrees of freedom, that's 4. And you compute that. When you compute here, you get Q4 equals approximately 6.4. And you look for chi-square 0.05 with 4 degrees of freedom, you find 9.48. And your rejection region or your critical region would say reject H0 if Q4, which is this thing, is larger than 9.48. But in this specific case, given the numbers that we got, we do not have enough evidence to reject H0. Why? Because 6.4 is no way larger than 9.48. Now, an extra question could be asked at this point. Given what we did in the previous problem, if I ask you in this problem to find the p-value of this test, what would you give me as p? How would you find the p-value? Everything is already computed. How would you find the p-value? Anyone to try?
So are still using the
Hmm?
standard normal distribution, they would tend to use that.
Probabilities are using the distributions that are in the test statistic. The test statistic has its distribution, and that's what you're using. In that problem, you used the standard normal because the test statistic was standard normal. You are going to use the distribution that is here, which is chi-square with 4 degrees of freedom.
I'm using 6.4.
Huh? You are using,
6.4.
yes, you are using chi-square and 6.4. So if you want to look for the p-value in this problem, you would say that the p-value, what is it? Probability that chi-square with 4 degrees of freedom is larger than 6.4. That's how you would translate that from the previous problem to this one. All right. Next problem is the same kind of table, but with a different meaning, the second meaning. Now you still have a table, but with a different meaning. You have 200 observations and 2 threads A and B. So now you are measuring every time you take an observation, you are measuring 2 things. That's what it means. So for you to feel the difference between this problem and the previous one, though you are going to use almost the same formulas, what is happening is different. In the previous problem, every time you picked an observation, you only had either 1 or 2 because they were not from the same distribution. You picked, and then you had all the options 1, 1, 1, 2, 1, 3, all to 1K. Or 2, 1, 2, 2, 2, 3, all to 2K. But here, every time you pick an observation, you have a value of A and you have a value of B. So you're measuring 2 random variables. You're measuring 2 random variables for the same individual. Does that make sense? You're measuring A and you're measuring B. In that other one, no. You are picking observations from A, measuring where they fall, picking observations from B, measuring where they fall. Setup is different. And you need to test for independence. Test for independence meaning what? That no matter where you're falling, the probability of AI and BJ is going to be the probability of AI times the probability of BJ. Technically meaning what? That if I restrict myself to a level of AI, the probability of BJ doesn't change. If I restrict myself to a given level of BJ, the probability of AI doesn't change. Does that make sense? So if I take the probability of AI in the whole sample, and then I take the probability at a given level of B, they should be same. That's what it means, independence. Which is completely different from what we were talking about in this problem. I'm saying all that, so we hope that you understand why I have an issue with the wording when you're answering the question and writing down the DFs and everything else that comes with it. Okay. So, what happened here? So, to answer this question, because we are assuming that the probability of AI and AJ is equal to P of AI times P of AJ, then we are going to replace in the formula of the high square P of AI AJ by P of AI times P of AJ. That's why we have this. And then multiply by N. So the probability of each of them is actually N times xi dot over N times xj dot j over N. Knowing xi dot, what is it? We define this as being the sum of all observations at the level xi. And x dot j is the sum of all the levels of all the observations at the level xj. Right? When you go through the second bj, when you go through bj and you add everything. And then when you go to ai, you add everything. And then when you multiply by n, that cancels one of the n's because it's supposed to be n squared. That's why you get this. And then you divide by that same product that is there, which is this. And in this case, the df is a minus 1 times b minus 1, which is 6 in this case. So you're looking at high square with 6 degrees of freedom. Alpha is 0.05, and then the number is 12.59. And then you compute the Q using the formula. You get that Q is 12.94, and your rejection criterion is reject H naught if Q is larger than 12.59. And you look at the Q that you got, and you see it's 12.94, and that is larger than this. Therefore, you would reject H naught. Now, same as in the previous problem, how would you find the p-value in this case? Hello. How would we find the p-value in this case? And so we are looking at I square with 6 degrees of freedom larger than what? Larger than 12.94. All right. Any questions on this one? No. Okay. Now that's the last question of this set. It's a question that is exactly of the kind we have here, test of independence. So it's 4.7.6 is same as this one. The only difference is that somehow we put in the formula a K, and the question is for you to find K such that the smallest possible K, such that you won't be, that you will reject H naught. So it's the same formula that is applied. And when you apply that, you get that Q with 6 degrees of freedom is equal to 8K squared over 3. So you easily add those things there. And alpha being 0.05, it's the same high square number that we have. So you would reject H naught if Q6 is larger than 12.59, same as there. And so you need to solve this Q6, what is it? It's 8K squared over 3 larger than 12.59, and you solve for K, you get that K squared is strictly larger than 4.72. So K is strictly larger than 2. So the smallest K is 3. Questions? Questions about this? Nope. See what the next guy says. So the next thing was about convergence in probability and consistency. So first question said we have yn follows the binomial with parameters n and p. Show that yn over n converges in probability to p. So how do we answer this question? First of all, you find the expected value. The expected value is equal to p. Okay. You find the variance. We know that it's n times p times 1 minus p over n squared. So it's p times 1 minus p over n. And then probability that absolute value of yn over n minus p is larger than or equal to epsilon is less than or equal, using the Markov inequality. Of course, I'm squaring this. That's why I do that. Expected value of yn over n minus p squared over sigma over epsilon squared. And therefore, this expected value is the variance, because we showed that the expected value is P. And the variance, we just found it here, P times 1 minus P over N epsilon squared. Now, after doing all that, you need to carefully show that that limit is equal to 0, not just tell me it converges to 0. That doesn't show me anything. So you got that the probability is less than distance. And you have to show not that this goes to 0, but that the probability goes to 0. So 0, less than or equal to the limit, less than or equal, because you have less than or equal to the limit of that. And this limit is equal to 0. And you still have one step. You have it between 0 and 0. Therefore, it is equal to 0. That's why you're concluding that the limit is equal to 0. Question? And this is larger than 0 because it's a probability. Probabilities are positive. Because just showing that a number, that a sequence is less than something that converges to 0 does not prove that that sequence converges to 0. If you don't understand the seriousness of what I'm saying, that's the point. Negative n squared plus 1 is less than 1 over n. The limit of 1 over n is 0, but the limit of negative n squared plus 1 is not 0. It's negative infinity. So when you're bounding something and you want to find a limit, you better make sure that you get it right. So it's very important to have that 0 there and show that they share the same limit. Now the second part, after doing the first part, here I don't need to do that much work as what I did there. Why? Because I gave you a theorem that if Yn converges to P and the function is continuous at the point P, then f of Yn also converges to f of P. That's one of the theorems that we had. So because I already showed that Yn over n converges to P, I take the function f of x equal 1 minus x. This function is continuous anywhere on the real line. Therefore, by this a that I just answered, this f of Yn over n will also converge in probability to f of P, which is the right hand side. But f of Yn over n is 1 minus Yn over n, and f of P is 1 over minus P. That's it, I'm done. And the same thing happens for the third part. I should take my function. F of x is x times 1 minus x. So this is what you have. It is a continuous function on the real line. No matter what you put in for x, that function is continuous at that point. Therefore, using the same a that I have there, I can conclude that f of Yn over n converges in probability to f of P. What is f of Yn over n? This. What is f of P? That. I'm done. Questions? There is no question. That's the last question that we had. Am I leaving you with this question till the first person that gives me correct answer to it? I have 5 points for that. The one I just showed. All right, so this is where we are. This is probably the last major topic that we'll be having, and everything else will be is applications of on different distribution, different cases. And we will not run into the other chapters that are there, so we'll probably be ending here. So last time we talked about convergence and probability, and today I want us to talk about convergence in distribution. So what do we call convergence in distribution? We say that a sequence xn converges in distribution to x, which are random variables, if and only if fxn of x converges to fx of x. Notice there is nothing here. It means it's just the regular convergence of numbers that you know for all points of continuity of fx of little x. So technically means that a sequence of random variable converges in distribution to a given random variable if the sequence of CDFs converges to the CDF of that random variable. And the notation is xn converges in distribution to x with a d on top of the bar. With a p on top of the bar, it means convergence in probability. With a d on top, it means convergence in distribution. And the two things are different. So, as an example, here, I'm looking at a sequence of independent and identically distributed random variables from the uniform 0 theta. And yn is the maximum of those observations. And I define Zn as n times theta minus yn. And the question is, show that Zn converges in distribution to Z, where the CDF of Z is 1 minus e to negative x over theta for positive x. And this, I remind again, we saw this last time, that's the exponential distribution with parameter theta. So in this case, we have n times theta minus yn converges in distribution to the exponential distribution with parameter theta. How do we show that? we find the CDF of Zn. By definition, probability Zn is less than, and here I don't really care about having strictly because it's a continuous random variable, so it doesn't matter whether you include it or not, but technically we need to include it. So probability that Zn is less than or equal to T, and I write down what that means, and I flip it, so I get Yn larger than or equal to theta minus T over n, and this is 1 minus Fyn of theta minus T over n. Yn is the largest of the observations, and we already have the formula in this class for the CDF of the largest of the observations. It is just the CDF of the random variable raised to the power n. And the CDF of the random variable in this case, x, uniform 0 theta, the CDF is x over theta for x between 0 and theta. Therefore, I plug it in and I get theta minus T over n, which is at x divided by theta by definition raised to the power n, because the distribution of the largest observations is the distribution of the population raised to the power n. So I get this 1 minus T over theta divided by n, and then raised to the power n. So if you remember your calculus, I remember maybe calc 2 or calc 3 actually, when you're doing sequences and series, it is shown in that course that this limit for any T and theta, this limit is e to negative T over theta. Okay? Therefore, the limit of the CDF of Zn is equal to 1 minus e to negative T over theta for T larger than 0. And that's exactly, this is exactly what we needed. And it is the distribution of the exponential random variable with parameter theta. Any questions? All right, so that's the first example of convergence and distribution that we have. Now, what can we say about convergence and distributions? The first theorem is this, that if Xn converges in probability to a random variable x, then Xn converges in distribution. The other direction is wrong. So convergence in probability implies convergence in distribution. This example, I got here. We know that X bar converges in probability to mu, which is the mean. That's what we proved last time, right? Therefore, X bar converges in distribution to mu as well. Isn't that scary? Then the next thing is, if you have xn converges in distribution to x, and yn converges in probability to 0, then xn plus yn converges in distribution to x. This is a very important moment for those who do research in probability or statistics, because sometimes you can show that a random variable is a sequence of random variables is equal to something plus a small quantity that converges in probability to 0. So you can drop that small quantity and just focus on the bigger part, because if you have that big part converges in distribution, then you will conclude that the whole thing converges in distribution. And it's important that this here is 0. Because if it's a random variable that is here, it becomes a different story. And then the next thing you have down there is for continuous functions as for convergence probability. If xn converges in distribution to xn, oh, I'm not putting the Russian D here. So, and J is a continuous function, then G of xn converges in distribution to G of x. So one of the rules that we do use there is what we call here the delta method. If we know that square root of n times xn minus theta converges in distribution to normal 0 sigma square, important, you have that square root of n there, and you have the normal distribution here. These two things are what leads to what you have here. If the function is differentiable at theta and j prime of theta is not 0, then if I apply the function inside to each of the things here, you can see what happened. So I just will apply g to xn and to theta. That will also converge in distribution to normal, which means 0. And the variance will be sigma squared times g prime of theta squared. An example of this is what you have here. Let's say we know that for an IID sequence with mean mu and variance sigma squared, square root of n times x bar minus mu, central limit theorem, converges in distribution to normal 0 sigma squared, right? So we know that. Therefore, I can easily show that square root of n times x bar squared minus mu squared converges in distribution to normal mean 0 variance sigma squared times j prime of mu squared. Because mu is playing the role of theta, where g of x is x squared, because I just squared this thing, it's x squared. J prime of x is 2x, and x When you plug in mu, you got 2 mu, right? Except if mu is equal to 0, that thing is not 0. Right? So if mu is not 0, then this thing is not 0, definitely. Therefore, square root of n, x bar squared minus mu squared converges in distribution to normal 0 and variance 4 mu squared sigma squared. That's it. And I don't need to worry myself. Any question? So when you have a question on that topic, what you need to do is to identify the functions that are applied and do this computation and plug in. But when you're doing your own research, you need to figure out by yourself what functions goes where. I was actually under the impression that when they switch the time, we should also switch the lecture time. Don't you guys think so? Look outside, it's nighttime.
You're thinking that maybe they will scratch it.
I mean, I'm not that impression too.
Well,
Well,
one that can scratch the maintenance.
I don't have that power. I get paid to stay here all the way to 1750. So I don't have a choice. So, anyways, we'll try to petition to see if they can do something about it. Everybody understands what I'm doing here? Do you have any questions?
It's not x squared. It's squared.
That's the one I raised to square. So that's f of this and f of that. The function is just squared. So in this example that you have, you just have to identify what is done to, what has been done to xn and theta to obtain the formula you have here. And that would be what the function g is. Before I do another example, before I go to moment generating function technique, let me actually have another example here. Find the distribution of square root of n times x bar cubed minus x bar minus plus theta. I don't know what I want to keep writing. All right, I give you 2 minutes to write this down. So find the distribution of this, stating a necessary condition of on mu. What condition should be on mu for that distribution to hold? Sufficient condition. That's technically asking to repeat the same problem I just solved for this other one.
X.
Right now, you done? You finished already? Oh, okay, so give me the answer. Oh, dear.
It's
That thing. What's that again?
3 square.
And what's the condition? Because there's need a condition on it. What's that again?
Plus or minus 1/4. Oh, 1/square root.
So your mu shouldn't be this. That's exactly what it means. Thank you. So, and you obtain this by just realizing that here, g of x is x cubed minus x. G prime of x is 3x squared minus 1. So g prime of mu now equals 0. 3 squared now equal 1. So mu now equal plus minus 1/3. And then you take that square into the formula. Pretty easy, right? But very powerful. All right, now the last thing that we had here was the moment generating function technique. How to use the moment generating function to show that a sequence of random variables converges in distribution to another random variable. And the theorem is that if the moment generating function of xn at t converges as a function of t to the moment generating function of x at t for all t is such that absolute value of t is less than h for some h, then that implies that xn converges in distribution to x. So you don't always have to take the CDF to compute the CDF of xn and find its limit. You can also, when you have the possibility, find the moment generating function of xn and find its limit. Once you find the limit, you identify the function that has moment generating function that limit. And then you conclude that the sequence converges in distribution to that random variable. All right. Okay, example. Let's say we have yn followed again binomial NP. and assume that mu equals n times p is constant. Which technically means what? That p is a constant divided by n, right? So p itself changes. P is a function of n. That's what it means in this case. And so we want to find out what is the moment generating function, the limit of the moment generating function. So find x such that yn converges in distribution to x. To answer this question, because we're in a section of moment generating function and we do know how to find the moment generating function of binomial, then we easily look at this and we say, easy, right? Myn of t equals, I've used this so much in this class, right? Is that what it is? Just say yes. Okay. So that's the moment generating function of yn, and we want to find the limit of that. And so this is 1, and p is mu over n. Plus mu over n e to the t, and then raise the whole thing to the power n. So that is 1 plus 1 over n times this is minus 1 t minus 1 raised to the power n. Do we agree? So myn of t, and this is for all t's, converges to what? What's the limit of this? That's what it means, converges. What's the limit? The same idea that was in the previous problem. This is 1 plus something over n raised to the power n. When n goes to infinity, what's the limit? It's that same old problem that I referred to Calc 3 for. Any help? E to this, that's the answer. E to the mu times e to the t minus 1. So that's what the limit is. And we do know that this is the moment generating function of Poisson with parameter lambda equal mu. So yn, moment generating function y of yn converges as n goes to infinity to e to the mu times e to the t minus 1. And this is the moment generating function of Poisson with parameter mu, which implies that yn converges to Poisson with parameter mu. So when the n parameter of the binomial grows the distribution becomes just like a Poisson distribution. That's what it means, right? That's why in some baby courses you have Poisson approximation of the binomial. If you take a Math 115 and Math 375, you might have seen those things. And this is the reason why. This is the proof of that coming out. You maybe use it 2 years ago. So for large n's, this is approximately Poisson. And there is another one that will take us back to the normal distribution. Any questions on this? Does it make sense? Now, I have a question. We've just shown that Yn converges in distribution to the Poisson distribution with parameter mu. And my question is, can we conclude that square root of n Yn squared minus n squared converges in distribution to normal within 0 and within sigma squared Can we conclude this? Hmm? Okay. I see a head shaking. No, no, no. So you need to be very careful when you're reading the theorems, because that rule, first of all, applies if from the beginning here you had square root of n times Yn minus mu. Secondly, in a convergence, and I will see this, though I'm explaining now. In a convergence, you cannot have n on the right-hand side, because n is the number that is going to infinity. You can't have that number as the limit or inside the limit. So for many reasons, this shall never exist. Find the distribution of Vn equal Yn plus 1 over n So if I ask you to find this other guy, what would you do? You would say, we have shown already that Yn converges in distribution to moreover 1/n squared Yn. Can I say this thing converges in probability to 0? Hmm? Can you show that it converges in probability to 0? Hmm? Convergence as n goes to infinity. Can you show that? How would you show that this thing converges to 0? All right. We ran out of time. So this goes to 0 in probability, and by our theorem, Yn plus 1/n squared Yn will converge to the distribution by the theorem that I gave earlier. And I need you to prove this. Thank you for coming today. That's the end of the road for today.
I do remember. I invite. Allora, senti,
What do you mean?